Good morning. I'm going to be going over this minecart launcher program problem. It's kind of a classic physics problem, and it's one that I think some students sort of understood was happening, and others sort of couldn't quite figure it out. So here's what's going on. Mr. Wimber is sitting here in a cart, and while he's in that cart, he shoots. The cart is moving forward at 5 meters per second. It's on a frictionless track, so it's not going to slow down. And he shoots a ball straight upwards. The launcher shoots things upwards at 10 meters per second. So when does the ball land? Does the ball land in front of the cart or behind the cart? And use our model to prove your answer. And when does the ball land? I don't think we'll get to the bonus today, but it's a fun one. So let's just think about this real fast. I'm going to go ahead and just start off with a motion map. We'll draw the ball with this sort of yellow color. So the ball we know is going to travel upwards, but ball is already moving 5 meters per second sideways. So you would imagine that every single second this ball is going to move 5 meters per second sideways and some amount up. 5 meters per second sideways, some amount up. 5 meters per second sideways, some amount up. And this just continues over and over and over again. Well, if we draw the cart, we'll go ahead and draw the cart as blue here. The cart does the same thing, just not without any of the up and down part. The cart starts off here, and then a second later is here, and then a second later is here, and then a second later is here, then here, then here, then here, then here, then here. And what we end up with is this interesting thing where the cart is always in line. Oops. See if I can get a good size here. The cart is always in line with the ball. So the ball is just straight above the cart, goes up, comes back down, and if it came out of the cart right here, and it's always just in line with the cart, it should fall just straight back into the cart. But I want to prove that. So here's what I'm going to do, is I'm going to make two different T-charts. We'll make one for the ball and one for the cart. So this will be the ball's T-chart, and this will be the cart T-chart. The ball will have a horizontal and a vertical. The cart will have a horizontal and a vertical. We'll start off with the cart's vertical because it's boring. The cart starts off at a position of 0 height, ends up at a position of 0, has no vertical acceleration, and has no vertical initial velocity. What it does have is it does have a starting horizontal position of 0. I do not know its ending position. It does not have a horizontal acceleration, but it does have a horizontal velocity. Similarly, let's go ahead and look at the ball. The ball has an initial position of, I'll go ahead and call this spot 0. I understand that it's not the same vertical position as this one. We could argue over if you want to call that a different name. Just for simplicity's sake, I'm going to call this 0. That said, if you picked a different number, it wouldn't affect your answer here. As long as you were okay. So if you called this spot 1, as long as you decided that I could catch it back here at spot 1 again, that would be fine. So I'm going to call it spot 0 though. So it started off at 0. It's going to end up at 0 when the guy catches it again. When I catch it, I guess. It has an acceleration of negative 10 meters per second squared, and it has an initial vertical velocity of 10 meters per second. Horizontally, again, we'll call this spot 0. It has an initial position of 0. I do not know its final position. Has no acceleration, and it has an initial horizontal velocity of 5. See, the ball here is moving with me. I shoot it straight upwards. It has a velocity of 5 meters per second. This thing right here is probably the trickiest part of this problem. See, the ball here is doing two things. The launcher shoots the ball upwards at 10 meters per second, but before the launcher even fired, the ball was already going 5 meters per second sideways. The launcher didn't affect that. The launcher just applied an upward force and had no effect on that sideways force. You've experienced stuff like this yourself if you've ever been in a car. Sitting in the seat of a car, and you could take a ball and throw it upwards, and the ball just stays with you. Even if you're going 40 meters per second, which is way too fast, you should not be going 40 meters per second anywhere on these roads around here, right? But even if you were throwing that ball up in the air, it doesn't, the ball just goes along with you at 40. And it'll go up, and it'll come back down. Well, that's the same thing that's going to happen here. I don't even really feel the need to do the math for this part of the problem, because I just want you to notice something. You see the horizontal sections? Look at the horizontal section for the ball, and look at the horizontal section for the cart. What do you notice? They're identical. There is no difference horizontally between the ball's position and the cart's position. They will always be in the same position. The vertical just doesn't even matter. The ball will go up and then down, whereas the cart won't. But horizontally, they are the exact same. We could prove this if we wanted. I'm going to go ahead, and what I'm going to do right now is I'm going to figure out how much time it'll take for the cart to come back down. So let's go ahead and solve this for some time. So I'm just going to go ahead and use this right here to figure out what time I would catch the ball. We know that y is equal to 1/2 at squared plus v naught t plus x naught. We know that, 1/0. That means 0 is going to be 1/2 times negative 10 meters per second squared times t squared plus 10 meters per second times t plus 0. I'm going to go ahead, I'm going to get rid of one of these t's just to make things easier. I'm going to move that 10.5 over here, so that's going to become 5 meters per second squared times t is going to be equal to 10 meters per second. T then must be 2 seconds. So this thing will be in the air for exactly 2 seconds, and when it does, my cart and my ball will have both moved horizontally. The cart, if it's 5 meters in 1 second, it will have moved 10 meters, and the ball at 5 meters per second will have moved 10 meters. In fact, both of these will be caught at 10 meters, the same horizontal position. This becomes much more tricky when there is a tilt, because what do frictionless carts do when they're tilted? They speed up. So this cart is going to now start to accelerate down the hill. And then I shoot the ball no longer straight up. Now I shoot the ball at an angle at 10 meters per second. So now the question is, when do we catch it? I'm not going to go through that right now. I think I'll go ahead, though, and put it on the key and post it. Try it out. It's pretty tricky, though. That is probably one of the harder problems I'd ask you to do all year. So don't worry about it if you didn't get it. But this right here is something, yeah, I expect you to be able to do. It's also something you can experience pretty easily yourself. Just next time you're driving somewhere, just take something, toss it upwards, and you'll see that it stays with you. It doesn't go flying backwards or forwards or anything. All right, everyone. Let me know if you have any questions. Have a nice day.